Averaging. I'm sure most of you think that averaging is a really obvious and easy thing to do to process your data, and you'd be right. But there are lots of different forms of averages, and the way that you calculate them can really help or hinder your analysis of your data. So we're going to start really simple and then build in a few different types that you might not have seen before. So the one that you're all familiar with is the arithmetic mean, where you take the sum of all your measured samples and divide it by how many samples you've got. So this is formally written in the equation on the right. If you apply this to a time history, you get the average value through time. And the more terms you have, the more samples you have collected, the better an approximation you have of your mean. Especially if you have a noisy signal, taking more samples will give you a better approximation. So, suppose we have this signal here. We have a static signal, which is blue. Let's draw this in blue. So this is in the middle. That is a steady signal. And then we have sampled this with some noise, which is red. So this is what our data might look like. You might be trying to measure blue, but you actually measure red with your data acquisition system. So the more samples you have, the more values you take to create your average, the closer you get to the true value. So if we look at the figure in the bottom right, we can see that what I've plotted on the y-axis is the percentage error to the mean. Now, because we know what the mean is here, because that's what we started from, we can calculate this directly. So the more samples we use in our average, the better the approximation we get. And we have a trend that follows this. If we do this 1,000 times or lots and lots of times and average the results, what we actually get is something that follows what's called 1 over root n relationship. So this tells you that so k is a constant that is dependent on the noise on your signal. It's actually dependent on the mean absolute deviation, which is just how variable your signal is. But what it tells you is that the more samples you have, the closer you will get to the mean with a 1 over n, 1 over root n relationship. So this is super important because it tells you exactly how diminishing your returns will be. So if we do this 1,000 times, like I said, you get the figure shown at the top. So this was the data from the previous slide, randomly sampled 1,000 times to produce the figure on the previous slide, and I averaged that 1,000 times. And this gives us a beautifully smooth 1 over root n relationship, where you can plot out what this relationship is. So what you can see from this is that if you want to halve your error in your estimate to the mean, you might need to do a huge number of extra samples. So having a plot like this really tells you whether it's worth continuing taking more data, which will take more time and cost more money. A different type of averaging is ensemble averaging. So this is similar to arithmetic mean, but you're now taking an average of something that varies in time, and you are taking the time into account. So your average, your x bar here, is still a function of time. So what does this look like? Suppose that you have this signal here. Okay, you have this bump, and you measure this signal lots of different times. You can average each individual time to give you an estimate for each individual time. So you produce an average that is time dependent. So this is really useful. However, you need to know exactly when these things happen in relation to each other. So your experiment always has to start at exactly the same time. If you have any variation, you will end up with something like bottom right here. So you can see if we average all of these data points together, all of these measurements together, to give us a time history, an ensemble average, we'll probably get something that looks maybe like that. And that's not representative of the real signal. So the reason for this is because there was a slight shift in the start point. This is known as aligning up or aligning T0. So it's really important you need to do this if you're going to try and do an ensemble average. So let's have a look at what that looks like. So suppose we have a noisy measurement of our blue signal, which is our true signal. And we take this measurement 100 times, and for every instance of time, we average our 100 attempts to create our ensemble average, and we plot that out. And you can see here in the middle figure, this is a really good approximation of the true signal. So we can plot this out like a performance map. So if we have the number of terms that we've used on this axis, we can see the more terms we add in, the smoother we get, the closer we get to the true signal, which is what we're after. Another way to investigate time histories is through using a moving average. So a moving average, we take a subsample of our measurement, we'll call it L. We take our L measurements and we average them together to give us one value. And then we step on in time by one sample, and we take L measurements backwards from then, and so on. And we repeat this all the time. So once we've created an arithmetic mean, again, we have an arithmetic mean of our little L samples, our window, that moves through time. So this is useful to give us a time history still, and it does smooth out the signal. So if we take a moving average of the top figure here, this is what we produced at the bottom. You can see this is a lot smoother. So it is a lot better at representing the true signal underneath. And you can do this in real time, but there is an issue with it. Because you're taking the previous 50 samples, say, or 10 samples, you're taking information from the past. So you will always introduce a time lag because of this. So you can see this clearly in the plot, bottom right, that our moving average signal is later than the true signal. But if you're doing this to present data live to the user, say in LabVIEW, maybe that's good enough. However, if you wanted to do this for a measurement after you've taken it, you can apply it in such a way where you don't introduce a time lag. So that's what this is. It's a very subtle difference, but one worth noting is that in the top corner here, the equation, instead of going from I to t, so from time I up to time t, instead we're going from t minus L over 2 to t plus L over 2. So we're taking half our window in the future and half our window in the past. And because of this, our time that our window is spread across is centered on the present. So when you take your moving average this way, you don't introduce a time delay. And that's what we can see bottom right here. This is usually called a flat average or a flat mean, just because we've taken each sample to be just as important. What you can do is apply a weighted average where you take different weights depending on how far away the sample is in time from where you currently are. So the way to do this, actually implement it, is via convolution. We're going to cover that in a couple of weeks' time. But that is a super, super easy way of applying this and changing the window function that you use. So instead of being a flat average, you can change it to Gaussian, you can change it to lots of things. But we'll cover that in a few weeks' time. Additionally, instead of taking an average, you could take the median. So if you want to take the median of a data set, you put all the values in your data set in numerical order, and the median value is the value that is directly in the middle of numerical order. If you've got an odd number of samples, this is the one in the middle. If you have an even number, it's an average of the two in the middle. So the median often doesn't give you the best representation of a smooth varying signal, but it does have some other really useful properties. So it is much more robust and it's much better at dealing with very large spikes and sharp gradients. So let's have a look at sharp gradients. Here we've got a square wave that we've measured in a noisy way. So we have our red samples of our blue square wave. If we take the moving average of this, what we can see is that the square wave is spread out. The gradient of the square wave is spread out. If we take the median though, it's not spread out. We have a really, really sharp edge here and a really, really sharp edge here. So the median, although it hasn't given us the smoothest response, has given us very sharp defined edges. Suppose, for example, we were taking a measurement where we had these red samples that we have at the top, but one of them was here. So if we had a measurement like this and we took the moving average, the influence of this really large spike, this outlier, would be heavily felt. So you would see it here. You would spread the influence of it out. If you take the median will remove this completely. So it is very robust to things like outliers. If you've captured lots and lots of data, maybe you don't need it all. So it's quite common to capture data almost as fast as your device will allow you, but you might not need to capture data at tens of kilohertz. So what do you do with it? Well, you can downsample your data. You can reduce the sampling rate. You can do this in a variety of different ways. The way that you implement this will have a really big significance on how strong your data shows noise characteristics. So the two common ways of doing this are called decimation and downsampling. So decimation actually comes, the term decimation comes from Roman legionnaires, where if they had behaved badly or they had done something incorrect, they would be split up into groups of 10 and they would be given straws to draw, and whoever drew the short straw would be killed by their colleagues. So every 10th person was killed. That's where it comes from. In a signals processing context though, what this means is that you take a block of your data and you reduce that block to a representative sample. So you could do this by taking the average, for example. So you take a 10 samples block or 20 samples block, take the average and put it at the middle of that point in time, and so on, and do it throughout all of your signal history so that you can reduce the sample rate. An alternative would just be to take every 10th or 20th sample. That's called downsampling. The negative of downsampling is that it is quite a lot noisier. It doesn't help with things such as noise on your signal, whereas decimation does, but it's a little bit trickier to program. So all the things that we've talked about so far have been averages. So they give us a steady quantity about a fluctuating thing. But the UK power grid follows this equation, A sine omega t. It's a sine wave. If you take the average of this, you will get 0. However, if you stick your fingers in a plug socket, you will be electrocuted. So the average doesn't always tell us what we need to know about our signals. So we do have alternative methods of analysing signals like this. One of them is called the root mean square. So the root mean square involves us squaring our data, calculating the average square, and then square rooting that. So what this tells us is some information about how much oscillation there is, what the power of that oscillation is. So this is the waveform of the UK main signal, and the RMS of this is 230 volts. So there is a derivation for sine waves. This is analytically known. Otherwise, you can calculate it on a sample by sample method using this equation. So the UK mains power is the RMS value. That's the value that's reported. So 230 volts. But because we know how this waveform varies with a sine wave, with an amplitude, the amplitude of this is actually 325 volts, which means that the peak to peak, so from a peak to a trough of our sine wave, is 650 volts. So just having one quantity might not give you enough information for you to really understand your signal, certainly not the average. So quantifying things such as RMS and understanding how they vary is really important for you to be able to accurately describe what you've measured.